The basic concept of stress is, of course, something that everyone in the entire world knows something about. Now, one of the fascinating things about this field of study is that we borrow a lot of terms from everyday life. And so that notion of stress, feeling somehow under tension or compressed or squeezed or something, well, that works out pretty well for us, but we're going to define it in very mathematical and precise terms. And we'll start with a general idea, and then we'll refine this progressively as we go along. Right? So this notion of stress is something about like the intensity of a force. It's not how you feel right before an exam or dealing with difficult professors. Right? So here, take this little sponge block, and I got this grid set up. And if I apply a specific value of force, but over a very small contact area, so that would be a contact stress, notice there's much different deformations that result than if I take that same force and I spread it out over a much larger area. Right? We don't have a load cell here, so you'll just have to trust me that I'm pushing with about the same amount of force. Much different deformation patterns, all because of spreading the load out in a different way, or smaller or larger amounts. Okay, so that's why you'll see here in this description about stress that it's an intensity of a force effect. We're talking about internal effects and or between surfaces, and it's critical to try to model how this force is distributed across a particular area. Think about your foot on the ground and a rainbow kind of stress plot, contact stress, kind of like a thunderstorm plot of you've got some real high stress points and some that are lower. It's not uniform across your foot contact area, right? But in a general or an average sense, then a stress is somehow some kind of a force divided by some sort of area. Notice mathematical, force over area. That means units of force over length squared. We'll get into that a lot more. Well, let's just talk first about different types of mechanical stress. Not psychological, but mechanical stress. Right? In general, we're going to categorize these in two different types of stress. Right? There's the normal, which means perpendicular to, and we use the Greek symbol sigma for those. And then there's shear stress, which is parallel to a plane with the Greek symbol tau. Not tau, but tau. Or actually, a real Greek might say tau. Right? Lowercase in both cases, sigma and tau. Normal and shear. Perpendicular to a plane or parallel to a plane. Right? So here's one of the basic, most simplest examples. Here's a bar that's being pulled apart. It has a cross-sectional area. We cut it in the middle, separate it out, expose that area. The internal force is equal to this external force in this case, so the axial force divided by that area is going to give us our normal stress. Right? That internal force being spread out, in this case in a uniform fashion. Simple model, may not be reality, but it's a simple model of where we're headed. And we'll come back to the equation for that when we start applying this numerically. Right? For now, we're just looking at different types. So that would be a basic axial stress. A torsional stress would be associated with taking a shaft and twisting it. Okay? So twisting a shaft will create torsional shear stresses. We have a transverse shear stress, which has to do with the beam, as does the flexural stress, right, which is also a normal stress. A bearing stress is the kind of situation you see down below, which you might say, what the heck do we have drawn here? What we've got is the ground level right here, right? And so this is an elevation view of looking in the ground. There's a building above. Here's a column on what's called a pedestal of a footing, right? So that's an axial force in a column coming down, and then the ground at the bottom of the footing is pushing back on the footing, providing the static equilibrium. That force from the column being spread out over that area that's on the bottom of the footing, right? You have to visualize that that might be a square pad that's coming out at you in the plane of the camera. And so there's a surface area in the bottom of that. So that column force divided by that footing area would be a soil pressure, and that would also be called a bearing pressure on the soil, and it's also a pressure that's being pushed back up against on the bottom of the footing. right? And then as a simple model down below, now we really get back into the shear stress idea. Here is a block that goes across two little pieces, two little supports, and we're pushing down on it. Now this little image shows that little block portion as though it's already started to slide or fail. It hasn't yet, but that's what it looks like graphically, just to illustrate what might be happening. This is called a punching shear, right? That this little piece is trying to be punched through those that little gap there between those two supports. We pull out that little piece here, and from an equilibrium standpoint, we have the total force here, and if we assume that we have some level of symmetry, then the shear forces that are parallel to those planes, that's key. Shear is parallel to, as opposed to normal is perpendicular to. These are the shear forces, and there's two of them because we have two areas that we're punching through. And so that's why you'll see over here that when we spread out that shear force in the average way all the way across that, that's why it's the average shear stress, we get tau equals V over A, and since V is equal to half of F, that would be F over 2A. Or you could look at it this way. This F is trying to punch through twice the area of just one of those sides. That's a simple or direct shear model. Right? Those are just the basic examples. In the next series that we're going to look at, we're going to perform some calculations on using these ideas.